Hello. Can you hear us well, the ones who are online? Maybe you can write in the chat. Yes, perfect. Thank you very much. We will start in maybe 1 or 2 minutes. Give some time for the people to join. Okay, so maybe we can get started. Thanks everybody for attending this seminar. It's my pleasure to host Simranjit Singh here. Simranjit is a research assistant in the Computer Architecture and Parallel Systems CAPS group at the University of Murcia, which is led by Alberto Ros, who is another good friend of the house. Simranjit just recently graduated from his bachelor degree last year in 2024 on computer engineering, and he's now a research assistant. And his research focuses on advanced cache prefetching techniques. He's also working on simulation frameworks for research in high-performance processors, and also implementing academic research ideas and proposals and papers in actual real hardware. In this direction, Simranjit did, he was awarded with a Severo Ochoa mobility grant, I think it's called officially. And yeah, so he visited us at BSc. We hosted him at the Encore group. He spent 1 month with us working on an RTL implementation of the Berti prefetcher proposed by Simranjit and the rest of the group at Murcia. And that's actually going to be the topic of today's talk, which is titled From Research to Reality, Integrating the Berti prefetcher into Sarganta. So please, Ranjit.
Hi, thanks for the introduction. And this is the presentation about the work as said Yuk, which consists on integrating the Berti prefetcher into Sargantana. It's a nice collaboration in between the Barcelona Supercomputing and the University of Murcia, because in the University of Murcia we have a, I would say, nice prefetcher. And here they have a lot of nice processors like Lagarto, Sargantana, etc. So first, I have some introduction of me, but since you have already told the most of it, I usually work with transfer prefetching. I try to match simulation results with real cores, and now we are working in this project, which involves implementing a version of Berti in a real core. So first, we should ask ourselves why we are here, what's the point of even researching these kind of things, prefetching. This is a graph which a lot of you already have seen. Is from Patterson, and what is telling us is that memory has been improving, but not at the same pace and the same growth that we have in other parts like calculation. We can do some calculations in picoseconds, but when we have to access some the main memory, it takes nanoseconds, even sometimes hundreds of nanoseconds, so it takes time. And the motivation behind this work is that hardware prefetching has been proven effective consistently in research. We know that hardware prefetching is effective, so we want to move the researcher pulses to a real core. This is challenging because in a real core we have new challenges. The area, the wiring becomes what type of data you have, the structures maybe needs to be simplified. We try to model those issues in a simulator, but when you actually are making this kind of integrations, you face new issues which you would have missed in simulation tools. And so the goal is to, do this move of some research proposal which seems to work and to a real core. So prefetching consists in the point of memory has some patterns going on, so we need to detect those patterns, and ahead of time we can prefetch those. And so if we can't go really faster, we can just start somewhat earlier. We need to ask what to prefetch and when to issue and to do. And in a prefetching, you have some metrics to note how well you are doing it. The best metrics, obviously, is the speed up you are getting, but some interesting metrics are the coverage, which gives you the information how much misses you are hiding. And accuracy is how of the total amount of prefetch you are launching, how much ends up being useful. And another very important metric is the timeliness. When you launch a prefetch, it is being launched on time? Are you launching before the actual data is requested? Because maybe you are launching at the same time or late, and that's not that much useful. So which patterns has the memory? The first pattern you will see is the simple crosswalk on array. You can access index 0, 1, 2, 3, and this one might be just covered by a next line. Next line is a very simple prefetcher. When you are accessing, for example, the line 3, you can prefetch 4, 5, or 6, and it works very well. Then you have the stride prefetcher, which detects constant gaps or distance between two axes that are conceptual. For example, here the difference is always 10, so the stride is 10, you access 10, 20, 30, 40. When you are at this point, you might launch 50, 60, or 17. There is the concept of delta. This one is used by for example, Berti. And the difference between the stride and the delta, the stride is the difference between two consecutive address, the gap we have here, and the delta is just the difference between one axis and any another axis. And this has some interesting properties. For example, it allows us to prefetch ahead of time. You can make the prefetch +8 when you are accessing 7, and then you are improving timeliness. But also, for example, a simple pattern like a crosswalk or a next line can become a more difficult one when you are in out of order core. So you are not really seeing the pattern like 1, 2, 3, 4, 5. You might see some other patterns there which can be detected by the delta, by using delta. Berti use the concept of delta to do prefetching, and it does there is some point of doing it at an instruction level. So Berti does prefetching, but see the history of access or deltas we were seeing earlier, but not at global level, but just in for one IP, one instruction pointer. It has a confidence-driven prefetching mechanism to only prefetch those which are useful, And for example, when in the case of Verti, we detect around 65% of when we have a confidence of 65% of time or coverage of 65%, it's a good idea to prefetch to L1. It tries to learn the timeliness, and it can also prefetch or detect the if it's what to try to prefetch to L1 or L2. He's proposed on the micro conference in 2022. So I will not go in much details about Verti today because we have changed some things in our implementation, but at a higher level, we have a history table which just tracks those histories of patterns of access we are seeing, and it then put the deltas we are seeing in the table of deltas. For example, here we are seeing like at the last two access to the IPA, we have seen this delta one time and this delta two times. So if we see the delta around 65% of times, we will launch the prefetch. We see that Verti works well. We tested in Jamsim, in Gem4Proc, which is our internal simulation tool in-house in Murcia. And it gets performance around 85% over mainstream prefetchers, which, for example, is Stripe prefetcher, and 33% of not prefetching at all in, for example, an alder like Core. And the accuracy is high because we see that about 90% of prefetch are useful, and we end up also saving some energy at the end of time. So when we are moving our task is moving Verti to Sargantana, which is third generation processor of the Lagarto family, is in order, is designed here. And here I had a lot of help for the Barcelona Supercomputing Group, Kim, Juk, Golnas, to understand how it works. And we need to make some simplifications. For example, Sargantana in the prefetcher mechanism tells us which address are being accessed. So we try to keep it simple, and we use only the information of the address to prefetch. We don't have here for example, the IP or another information we can have in simulators like Jamsim. In Jamsim, you have a virtual address at L1. You can have a lot of things with the hit is the access is a hit or is a miss, etc. So we wanted to start simple and use only the address. We have seen that the page, we can use the page of the address as the context, as the IP, as we used in the Verti. So we don't track IP, we will track using the page. Then we will ask ourselves when we are accessing this page, which block is the next one to probably be accessed next. So we try to find those patterns between the page address. So I will start explaining a little bit better how we are doing these block patterns. We are finding those block patterns. We just get the idea of Verti. We have a history table, we have a delta table, and we have a prefetch queue. This is marked as a question. I will tell why, and I will go now into details how this works. The history table has stores which page and which block has been accessed. The replacement policy is pretty simple. The first thing to enter is the last entry to get out. So, and it will output the deltas. I will explain this a little better in the next, in the following slides. So this is really the concept. We will output the deltas to the delta table, and the delta table will manage the deltas and launch the actual prefetch. Now we are using registers, but we will use SRAMs in the final version of this history table. So this is how the history table looks like. It's something, it's a table like this. In each, when we are starting, all entries are invalid, and when some access happens, we will just set the history, we will store the as an entry, and we will store the page and the block. As there is no deltas found now, we will output nothing, zeros. Zero means invalid. So when another access happens, what we are doing is a simple rest. We will search for same pages in the same set, and we will output the deltas for this page. In this case, we are detecting a delta of 2 for the page 0, so this will be the output of the history table. I will explain now afterwards how it works, how we use those deltas to actually long prefetch. If a hit happens, that means we are seeing again the same address we have seen earlier. We will do nothing because we already used those deltas and we already did the necessary computations. So the delta tables will use the deltas output from the history table, and it has some a global confidence counter, which is how many this IP address or this page in this case has been seen. Then it has up to n deltas, and per each delta, how much confident are we are, how many times we have seen this, and a prefetch flag. Then the replacement is again very simple. 15 entry of the page is the first, is the last to go out. Here we will output which blocks in this page we want to prefetch. So, for example, we see this zero deltas. This is how the tables look like at the start. We have a valid bit, the page and global confidence, and the delta list, and then we have the deltas we have seen. In this case, we have not seen nothing. So after the first access, for example, we might have seen a delta of 2. That we will just store this delta for the page 0 because we have seen it at one time. And then if the same access happens again, well, we will increase the confidence or the amount of number of times we have seen this page and increase the confidence. At the end of the day, the confidence of a delta is how many times we have seen this delta for this page in this number of times we have seen this page. So again, we can see another delta. We will increase we can see multiple deltas. For example, we see 2 and 3. Then we increase the confidence of the delta 2. We will add the new delta in this table. And again, we are again seeing new deltas. We see now the delta 1. We add it. We see the delta 2. We upload the confidence of this delta. We see the delta 3, we upload the confidence of this delta, and we count how many times we have seen this page. When the confidence of amount of times we have seen this page gets to a point, which might be in this case 4 times, we will see how many deltas are above a certain threshold. For example, in this case, the delta 2, we have seen it 3 times, so it's enough to next time use it as the prefetch value. And the another ones, we will just discard them. And how we are issuing this prefetch. This is, I will say, a nice way to do. We use the block address. We submit the delta, in this case 3, well, we sum the block address 2 plus 1, which is plus 2, which is the delta, and it gives us the index 4. We want to prefetch the index 4 within this page. So the prefetch queue, I will explain how it used this output, which might be seen a little bit weird, to actually issuing some prefetch. The prefetch queue stores the page tag and a block bitmap. It means if it's in this page, I want these blocks. And we'll do a coalescing in a push. We'll search for this tag and just do the OR for the number of blocks we have already in the, if we have the matching tag, we will just save those blocks we have already in the fetch queue, and we will add the newer ones we are seeing. The size of the fetch queue is pretty low. We see at the 2 or 4 or even 3, 2 values are pretty good. So we don't need much tags. We can store little entries, but we can issue a lot of prefetch with just 2 entries because we are storing the blocks in a bitmap. So we can also, when the prefetch queue is full, we can pop the 1 entry in the prefetch queue or discard the new prefetch as we want. We can try to figure out which works with the better and use it. So let me explain how the fetch queue works a little bit better because it might be something confusing. We have the page, we have the index of the blocks we want to prefetch. So it's as simple as, in this case, we have the index 3. It means I want to go, well, index 0, 1, 2. I will search the first one in the bitmap and add it to the page address as list. So I am prefetching the page for A with block 2, and the offset of the block is 0 always. So this way we save a lot of space because we are not saving actual addresses. We see it works well in our simulations. First, we tried this idea, this proposal in our simulators to see how this works. And there are some numbers, for example, in Gem4Proc, for the spec suite, we are getting around 9% for this version of Berti. We are getting 5% in Jamsyn, and which is actually kind of near the performance of Berti. Then we modeled a Sargantana like core in our simulators, and we get more because it's Northern, and we get like 34% for spec, 6% in gap. We see that Berti is adapts more in different type of suites than Berti, this subset of Berti, but it also can get a really nice performance we are seeing. So now in our implementation, we are getting these numbers, but these numbers are fairly, I will say, on study. We are doing a lot of work in hardware, so these numbers are not really useful because they are changing week by week. So last week we had one number which was like 6%. We see some bugs, and we improved to 9.7. And which is nice is there are some traces, some benchmarks where we do really well. For example, we can see in the MTSP-MB, we are getting like 40%, but that's not the nice thing. The nice thing here is there are some benchmarks we are getting really slow down or little performance. For example, the matrix multiplication, we get like 0.9. And with a stripe prefetcher, we get a lot more. So that's really nice because that helps us to understand what is not working here. And we are using those benchmarks that are not working to actually look at and see which are the bugs or which are the improvements we can really make in this prefetcher to improve, to detect bugs, and to, at the end of the day, get the desired performance, which are we expecting with our simulations. So The conclusion, this is an ongoing work, and I will say one of the conclusions is we are simulating when something is not working or something we want to see which is the range of deltas, how many delta we are issuing, how many prefetch queue size we need. It's just fast to simulate, and it turns out it works when the numbers are kind of similar when you see at the hardware level. And the second is to simplify. You need to really simplify those big structures you have in the simulators. For example, searching some value in hardware can be very costly, and you can do it really easily in some simulations. So you need to adhere to look like how this will turn out in hardware and simplify those structures you can simplify without losing much of the performance. And the nice thing with the prefetch queue is I have seen in my experience, at least for me, that prefetch queue in simulation tools like ChamSync or in-house simulator is a different entity. It's part of the prefetcher. So you really don't optimize this. So you just input the addresses and that's all you are doing. So you are saying to the simulator, we want to prefetch this, but you can optimize the prefetch queue to be more relevant or more near to how the prefetcher works. And then you can have a lot of more space with a lot of less size. But this applies like with any other part, actually. And well, the silicon, when you implement it at hardware, is the last task because you really get the performance here. And in simulation, is something you are testing. It works, it will not work, but here you can make a tape out of a processor. And lastly, thanks everyone to come, and thanks for Kim, you, Colnas, Alberto, and Agustin, who have been helping me in this task a lot, and I think we are doing a good work. That's all.
Okay. Yes. Thank you very much, Kim. We will start with some round of questions for the audience online. If you have any questions, you can write them in the chat. I will read them out to Sim. And Sim, if somebody from the room asks something, which we have already some hands raised here, please repeat the question for the people in Zoom so they can hear it well. Okay.
Okay.
Thank you.
Okay, so I have a couple of questions. So first of all, of course, it is very important that you investigate why the velocity performance in some cases, but also I think it's very interesting to investigate why you get 40% of improvement, no, in SPMD, for example. Can you elaborate?
Yes, that's actually the very good question. Why we are getting the dash performance, and we are playing the delta concept, and we are tracking, so you can actually see more patterns there than with a stride. But I will don't rely with this number. So why we are getting this performance in the I mean, I will not rely with the numbers we are getting in the hardware prefetcher to up to today, because it can be really randomly. Because why are you getting these numbers? You can getting these numbers because you are prefetching the whole page and it end up being useful at the end of the day. But the core idea of why we are getting this performance is because you are applying a lot of concepts we seen in Berti that works. For example, the concept of delta, the concept of seeing those patterns at a local level. For example, in the example you see next line in out of order code might be not working that well, and Berti does work better.
It's a combination of multiple factors.
Yes.
Essentially, that gives you
Yes,
more
and
performance.
actually it's a good question for me, not only to investigate more of why we are getting those numbers. We really should look like, and I do look, and most of time we are in Harvard, we are seeing we are getting these numbers because we are getting we are getting some strides and some patterns that work. For example, in in some benchmark I have seen, we are seeing like a pattern of +2, +4, +6, +8, and it ends up being useful.
So a second question, please, is, if you compare with your micro 22 paper, also in the simulation versus RTL implementation, what is the difference? What did you get?
Yeah, we are
in
ongoing.
terms of performance?
That's the whole point of doing this, and we want to compare. Now, since we began with this implementation like 15 days, 1 month ago. So we are in the phase of implementing and adapting some numbers. So we are using the simulation to detect
Yeah, I
what
understand,
can
but
we.
More or less, you are in line with the simulation performance, or is your service deviation? I assume the second one.
We
because
don't.
it's
Oh,
working
sorry.
well, or no?
If we see the numbers here are bigger. So we get more performance here in the simulation tools for this suite
So that means
and
that-
less
yeah,
than. So the good thing we should do now is to use this benchmark, which we can import to the simulation and see which is the difference.
Yeah, yeah.
That
That's
will
good
be
actually.
the very next step, and I think it's the good way to do.
Nice work.
I think it's important to clarify here. This is ongoing work.
Yeah,
So all these are RTL
Yeah.
simulations, the environment is kind of limited when you do RTL simulations, small input sets, no virtual memory, all these kind of things, right? So, and the numbers you see on the simulated, with high level simulators are full benchmark suites and so on. So the setup is very different. You cannot, it's not an apples and apples comparison. One of the nice things that's on the way, that's hopefully we'll be able to do soon, thanks to the work of some of the team members here, is to put this on an FPGA as well. And try to run something more similar to the SpecSuit, CAPS, all this kind of well-known benchmarks, right? That's a much more fair comparison as well. But yeah, as Sim was saying, this is ongoing work. And those numbers are very initial.
Yeah.
I think you got double the speed up in 1 week. Last week we were not at 10%, and now we're at 10%, and next week we will be higher, hopefully.
Yeah, this part of the limitation that you mentioned before, the others set up size with.
I don't know if there's any question from the audience online. I don't see any in the chat. If you have any question, please write it in the chat. I do have a question. It's not necessarily technical, but on the work philosophy we've been following, and I know the answer, but I think it's interesting because here we have a good mix of people working with high-level simulators, proposing things on the more academic side of things. And then we have other people working more at the RTL level, doing more like implementations towards tape outs, etc. So can you talk a bit about your experience in bridging this gap, in going from taking a piece of work that is published in Micro 2022, bringing it to an RTL implementation? What the steps have you followed? What have you learned? What can be useful for people here that is working on both levels?
Well, when I do work here, I really try to simplify what we are doing here, and then explain, well, in RTL I have implemented this in a higher level to those who are working with the simulation, and they usually say me, okay, if you do this, this is not correct, change it. So, and with an RTL level, and they help me to implement those things that the in simulation tools they find is useful. So they in RTL level they are just saying, for example, don't do this because there is a area cost of or a complexity cost, and then you talk with the both teams and you get like see the trade-offs and do more simulation and improve your simulator. So it's kind of I think it's a good work because this way we are improving our simulation tools because we are actually seeing what differs. We know to simulate better and get more accurate results. And also, I think we work faster this way because you can abstract actually the level of RTL, the code itself, and then explain like a higher level to one team and then connect and bridge the team, and you are kind of doing a bridging, and that's nice because at the end of the point of doing research is to implement it.
So, by the way, the tools that you've used is OpenPython and System Verilog or something else? That one?
Yes.
And along the presentation, you also commented that, for instance, in the interface between the core and the prefetcher, in the high-level simulators, you assume you have lots of information and so on, but in the RTL, you don't have any of that. The same when you were talking about the prefetch queue, that in the high-level simulator, you can do more co-design with other parts of the architecture. Here in RTL, we've been a bit more limited when it comes to doing that. You have modeled all that in high-level simulation. That's what you call the BERT-PSC in those slides, right?
Yes. Yeah.
And
Not the whole bunch of things, but because we are seeing new things coming up and then we are implementing this, but good part of this we are trying to match the simulator to the real code. But there is a point. For example, for the code design point we have seen in simulation, it's the other way around. Because in simulation, that can be something for me because I don't know the rest of people, but I see it like something totally different. When you really go to the RTL, it comes up, the prefetch queue is part of the prefetcher. So you can use those concepts and you can actually make some tricks on the prefetch queue. You can, if it's a stripe prefetcher, you can change how the prefetch queue is. If it's a Berti prefetcher, you can change how it is to adapt to that prefetcher. In simulation, you can do it obviously, but there is a layer of abstraction, and it's might be easy to say prefetch queue is something apart. So when you go in RTL, you can find that there are some code designs you maybe have not thought about in simulation.
very nice. And generally speaking, how different are the versions in your high-level simulations, like the real Berti from BERT-PSC that you called in that slide? What are the main differences?
The main
that you have
difference
found?
are because you don't have for example in access you don't have the information if this access is a hit, is a miss, or a prefetch hit, for example, and you cannot rely in this in the history table. Berti only sees misses and hits due to a prefetch, don't see hits. And then, for example, the address is virtual address in simulation tools, is physical in RTL, but as we are also working in this kind of stuff because, for example, knowing if this is a hit due to prefetch, it might be more costly, but you can incorporate some changes to the interface, and we are working to use virtual addresses in in the RTL. Another difference is you don't have timestamps to be more timely. In the MSHR, BERT has some extensions and has some timestamps you don't really have here in. So, and that's will be another difference. And then we get some differences. For example, in the case of the delta table, we have to do some modifications which are ongoing. So that's because I have not really talked about them, but we are doing some modifications to avoid search the delta and just to find it using I don't know the index of where it is. So there are differences between BERTI and BERTI BSS. There are similarities because you use the concept of delta, which is used again in BERTI. You use the history table as a similar concept of BERTI. You use the delta table in a similar way you do use in the BERTI, and the prefetch queue is different. And there are some downgrades because you don't have some information. But when you are building, you can also find some things that might be useful and might be more a little better. Turns out in REA in RTL.
Yeah, that's really good. That's now that is Sargantana people here. Maybe we should give some feedback as well to this information that we don't have. In the RTL, hits, misses, all these things, timestamps in the MSHR. Maybe that's good feedback also for the RTL teams. If we believe that's beneficial, yeah, maybe it's a good opportunity now to give some feedback to some of the teams. Yeah, but this exercise is great, as you say. You can either adapt your design of the prefetcher, which is what you have been done. That's one thing. Well, that's one way, and the other way is ask the other teams.
So you can see the trade-off each feature. You can
exactly, and you can pick up individual aspects and what does this hit or miss information gives you? It's this percentage. It's worth or not putting. So that's very interesting, fine-grained information that I think is very, very interesting. If there's any question?
Well, I have one more question. I know the answer because we've been working together quite closely, but regarding a quite important parameter of the prefetchers is the timeliness. And we've been discussing how it could affect implementation and all the different implementation methodologies that we can take in order to apply some timeliness friendly strategies, and if BERT is really affected with that timely variation, or if it's more abstract to it and it's not really important for BERT. You get
the question is how, if the timeliness is important, is not important, how you can make the timeliness more to be more timely, the prefetch itself in RTL. That's the question I will say. And that's a nice question because you can this is the aspects you need to test to answer. I will say what happens when you retire the timestamps, because then you have delta and you are seeing more deltas, and maybe you are issuing more prefetches, but some of them are timely, some of them are less timely but rather useful, and how that the changes affects and how you can make it more timely. I will say the best thing here, you can simulate to these restrictions, to simulate with this restriction to see how it affects, and you can kind of get an idea of which direction to go or not to go.
And maybe just as an idea, BERT doesn't really care about the timely of for the confidence in order to be fetched.
Yeah, it cares. BERT cares. Our version does not care, but the BERT itself does cares about timeliness. It can discard prefetches based on the information
right
of time.
And then just another this is more of a clarification I wanted to do, is regarding a very important, and in my opinion, is a must in the implementation of any hardware piece at the RTL level, which is the parameterization. It's also important to note that this work has not been yet fine-tuned. So the parameters used are the basic that you found, like the baseline that you found that could work on simulation of high-level simulations. But I think it's important to know that we still have to find what's the best trade-off in between area, power, and time, cycle time that we can achieve.
Yes, actually, we need to fine tune the clarification is we need to fine tune the parameters of this prefecture to get the trade-offs of increasing this table and against the area it will consume, and even other parameters like when to issue these prefetch at what level of confidence affects a lot, and we need to fine tune to see which are the best values. And you might this is a question of trade-off, but it's also a question of the just fine tuning some values without any trade-off in area to see how they work. And we are not this step, we are using some values that we have seen that works well, but we are using actually blindly because we need to test which are the best values.
Future, are you planning also to experiment to implement the prefecture of one level of caching, like in the private cache here, 1.5?
Yes, that would be nice. One of the main characteristics of Berti is Berti is seated in L1, but it does orchestrate prefetches to L2. If I'm not mistaken, the authors of Berti have tested to prefetch to LLC, and depending on the confidence, they don't get much of they have seen the best way to do is place the Berti at L1 and then orchestrate the prefetching to L1 and L2. This way you don't need two prefetches, you only need one, you can see everything. And yeah, also there are some trade-offs because you have a one prefetch queue, one port, and L1 and L2 you can have maybe more ports, and you are not using the same ports. There are some trade-offs, and we need to evaluate those changes, but it's a nice future work. Not only put the prefetcher in L2, but also see what happens if you have a prefetcher in L1, what happens if you have a prefetcher in L2, what happens if you put the prefetcher in L1 and don't bring the data to L2 to L1, just get it at L2. Even combine, for example, you have one prefetcher at L1 and and another in L2, which is, for example, detecting chase pointer, and you have a Berti with another kind of different prefetchers, and that is detecting different patterns. And I will say that there is some work to do there.
Okay, are there any other questions? I don't see any in the chat. I hope you can hear me. If anybody has a question, please write it. Otherwise, there's some more questions here in the room. So maybe we can thank the speaker again, somebody. And yeah, thank you very
Thanks
much.
everybody.
Thanks everybody for attending. We're closing the session. Bye bye.